Hello, and welcome back to the course. Today we'll look at Cauchy's formula in a disk. So this is a special version of Cauchy's formula, but actually it's already really useful. Maybe it's the most useful version, even though it's a special version of it. So this is subsection 3.2.4. All right. So this is perhaps the most fundamental term of complex analysis. It's the more general one, I guess, but it's it will be basically all that we're doing is right now we're just doing it a disk for a circle, and so later on we'll do it for other cycles than just a circle. But it's essentially this is the theorem that we're proving, and this really makes holomorphic functions tick. This is the formula that gives them all their sort of magical properties. So said we'll prove it in a disk. So what is the formula, right? So suppose we have a holomorphic function in some open U, and let's suppose that there's a whole closed disk inside U, right? Then for any z in the interior of the disk, so for any point in the interior of a disk, we have that the value of the function at that point equals this integral, which goes around the boundary of this disk, right? So we're evaluating the function divided by zeta minus z, integrating with respect to d zeta around the boundary of the disk, right? So we're only evaluating f on the boundary of the disk. We don't care about its values anywhere else, and we get the value inside. Now this should be surprising. The values inside, which is a very large set, is the whole disk, right? It's this two real dimensional thing, right? It's part of the plane. Those values are given in terms of the values of f on a relatively small set, on just this circle, right? On just a curve, right? Once you know f on the curve, you know f inside, right? F cannot be anything else. Once you know it on the on the circle, yeah, that's it. You know all the values inside as well, right? So that should be surprising. This shouldn't, this is not going to be true for an arbitrary function. If you have a continuous function, no matter what it is outside, inside, it could be all sorts of stuff, right? You have no control over a continuous function in terms of its values on the circle, right? But for a holomorphic function, once you know it on the circle, you know the function in the disk. Now, and this is hardly going to be the main application. This would, it wouldn't be at all an important theorem if this was the only application, but you can actually use it to evaluate some integrals. So for example, if you have a integral like this, cosine of z squared divided by z over z minus 1, something like this, and you're integrating over some circle, then you can actually use this theorem to, like, for example, if it's a circle around 0, not including 1, then you could think of cosine z squared over z minus 1 as your function, right? And then you'd be evaluating that at 0, right? So it's so that's one small application of it. It can be used to evaluate integrals, but really that's not its main use. Its main use is sort of theoretical. That it's it's telling you how how holomorphic functions behave, and essentially everything that we'll do from now on is going to stem from this theorem. All right, so let's prove it. Let's start with some point z in the disk, and let's make things simpler so that I don't have to write down the circle, the circle radius r, so that I don't have to keep writing it down. I'm gonna just call it gamma, right? That's much easier to write down, right? And as usual, we orient it counterclockwise, right? Now, I mean, we did that in the statement of the theorem. I didn't quite mention that, right? But all of these things are always oriented counterclockwise, right? That's the way that that we set things up. All right, so let delta S around Z be a small disk around Z, right? Z is some point in the big disk, and this is going to be a small disk that completely sits inside the big disk, and actually the closure of it sits inside the big disk. I want the circle, the circle of radius S around Z. I want that to be inside the interior of the big disk, right? And I'm gonna, again, to make things simple, I'm gonna call it alpha, right? So I have a gamma and I have an alpha, right? My two cycles. Now what I'm gonna do, right? So I have Z somewhere here. I have gamma is out here. I have alpha out here. Now, what we're gonna do is we're gonna connect the two, alpha and gamma. We're gonna connect it with these two straight lines, right? You could just take this, they could be on the line through 0 and the origin, or 0 or p. Right? So just it doesn't have to be necessarily that, but yeah, you could do that. So connect it with these two lines, and basically think of two new cycles. Think of cycle C1, which is this guy, right? And think of cycle C2, which is this guy, right? Now, the thing to notice, or actually two things to notice, is that if I integrate around these two cycles, the integrals over here cancel out, right? I'm going this way for C2 and this way for C1, and this way for C2 and this way for C1, right? So those things that I've added, well, they cancel out if I take both integrals, if I add up both integrals. The other thing to notice is that if you look at, for example, C1, right, you notice that it doesn't really go around Z, and that's the point, right? I have now two cycles that do not go around Z, right? And so as chains, we get this, right? I have, for alpha, I have to be going in the opposite direction now, right? So that's why I'm saying minus alpha, right? If I want them as these guys as chains, right? Because if I'm going around C2, I'm going this way around alpha, right? And if I'm going around C1, I'm going this way, right? So I have to go clockwise around alpha. So that's the reason for that minus sign, right? But we have that C1 plus C2 is gamma minus alpha. All right. Now each, C1 and C2, they both lie in a star-like domain. I've drawn two of them here, but they're not. Those are not the only choices, right? So, for example, C1, you could take this star-like domain over here. Maybe it doesn't completely look star-like if I do it by hand. But yeah, it's star-like, and it doesn't include Z, right? It would be star-like with a point somewhere here, right, with respect to that point. But it does not include z, and that's the point. Because then this function, the thing that I want to integrate in Cauchy's formula, that function is holomorphic in this domain over here, right? It doesn't, because thinking of it as a function of zeta, right? Because zeta is never z, so yeah, this is nice and holomorphic, right? All right. Now the same thing for C2, right? And that's the other other line over here, right? That's the other guy, right? So both of them lie in a star-like domain. A different star-like domain, but both of them lie in a star-like domain. So we can use Cauchy's theorem for star-like domains, right? And we have holomorphic function, which is holomorphic in these star-like domains, right? So if I have S chains, I have this, right? That means that the integral around gamma minus the integral around alpha, which is the integral around gamma minus alpha, is equal to the integral around C1 plus the integral around C2. Now, both of them are zero by Cauchy's theorem in star-like domains, right? I mean, both of them will use a different domain, right? But that's fine. That's okay. So both of these are zero, right? Meaning the whole thing is zero, right? Meaning this integral is equal to this integral. That's the point, right? Now, the key thing here will be that this gamma, that was, what made it hard to evaluate is that, as you'll see once, on the next slide, is that it's not centered at z, right? Whereas this alpha is centered at z, which will make it easy to evaluate. Okay, so, right, as I said, the two integrals are the same. Now let's parameterize alpha. Let's actually compute alpha, right? So it's, I start at z and then I go, right, it's of radius s, right? So I have e to the it times s plus z, right, is my parameterization for t between 0 and 2 pi, sorry. So let's say, or minus pi to pi, however you want to do it. So I have that this integral is by definition, right, I write down what d zeta is, right, that's this guy, because if I differentiate over here, the I comes down, the z vanishes. The zeta, right, that's this thing, right, and then here, right. Now notice, this is why it's easy to evaluate if the circle was centered at z, right, because this z cancels this z, right? The z in the integral is cancelled by the z coming from the parameterization. All right, and then there's a couple more cancellations. This s e to the it cancels the s e to the it here. There's an I left over, so that's why this I just disappears. It's not here, right? And I get this integral over here, right? Which is really the average of the values of f on the circle of radius s around z, right? That's the averaging integral, right? And anyway, right? So this integral, the integral around gamma, which does not depend on s, right? S was just the radius of this small circle around z, right? So alpha depends on s, but gamma doesn't depend on s. Nothing in here depends on s, right? This guy depends on s, So that means it's the same thing for all s, right? I can take s, I can take arbitrarily small s, and the integrals are still equal, right? So I can take a limit, right? I can take a limit of something that's constant, right? That's basically the idea, right? So this limit, as s goes to 0, the limit exists. Well, because it's a limit of constants, right? So this integral that I'm interested in, that's the one I want to compute, is equal to, well, it's equal to all of these, but yeah, I'm taking a limit as s goes to 0, right? I mean, that's equal to that as well, right? Now, this integral, let's write it like this, right? That we just computed, right? This average of the values of f around this circle of radius s. Now, by continuity, if we're taking s smaller and smaller, right, that limit, just for any continuous function, right, this is true, right? That will be true for any continuous function, right? Not just holomorphic function. For holomorphic function, it actually equals this thing, right? So because we're averaging the values of f, in smaller and smaller neighborhoods, well, it's continuous. Those averages go to the value of the function, right? So the value of the function is f of z, right? Okay, that's it. This is equal to this, right? That's the theorem, right? Maybe let's, just for completeness, let's look at it again, right? There's very little, there's very few extra hypotheses here. It's an open set that contains this closed disk. I mean, we do want to integrate over the boundary, and we have a holomorphic function. That's it, and we get this formula. Now, there's going to be other versions of this. You could have just a function that's maybe continuous up to, so continuous on this closed disk and holomorphic inside. That's going to be good enough by taking limits, right? So sometimes this simple version is stated that way. So this is a simpler version of the simple version. All right. So let's look at a very useful consequence, something that actually came up in the proof, and that's, as I said, for any continuous function, you always say that the limit of the averages goes to the value of the function. But for a holomorphic function, it's actually always equal, right? Because we're taking a limit of a constant, right? So, and this formula also just it comes up if you just apply the theorem, right? You get this formula if you apply the theorem with z equals to p, right? And you compute what that integral is in terms of sort of the standard parameterization over this disk. But it also came up in the proof, right? I mean, we actually did, we evaluated that integral, right? So that's a neat thing, right? And this will actually come up a bit later. That tells you something about how holomorphic functions behave. That they're actually this really is something about them being so-called harmonic functions, functions which are averages, whose values are averages of the values in little circles, right? So one thing that will follow from this is that such functions cannot achieve maxima, right? well, at least either the real or imaginary part or the modulus, right? That will actually come up, that will come from this formula over here, right? This is true for all arbitrarily small r, right? All right. So next time, what we're gonna do, we're gonna look at one of the big consequences of Cauchy's formula, and that's to show that holomorphic functions are actually analytic. We're actually gonna compute the power series for holomorphic functions. So we're gonna show, we've already shown that analytic functions are holomorphic. So we're going to show that holomorphic functions are analytic, right? They're one and the same, and that has really profound consequences. And it's a consequence of the Cauchy integral formula. That's sort of the main thing, right? Which is a consequence of Cauchy's formula, all right? So, all right. So, see you next time.